everyone, my name's Julie, I work here at Vibes, and today I'm going to tell you a little bit about the Vibes approach for doing sound and vibration engineering. So you know when you're driving down the road and you hit a certain speed and your car just starts to shake? Or maybe you're driving at a constant speed and you hear some annoying buzzing coming from somewhere in the back. Well, these are just a couple examples of the types of problems we like to study here at Vibes so that we can avoid them or hopefully at least minimize them. So there are two components that are going to affect what you hear or feel inside of the vehicle. First, we're going to have the forces coming into the vehicle. Maybe they're coming from tire road noise, or there's a specific electric component that's causing its own vibrations. And second, we're going to have a transfer path between those forces and what the driver hears and feels inside of the vehicle. So both of these components we like to study in a unique way here at Vibes, and that's what I'm going to tell you about today. Let's start with the forces, and let's take the steering gear as an example. Say I want to understand the forces that the steering gear exerts on the rest of the body during operation. I know what you're thinking. Let's just put some force gauges between the steering gear and the rest of the body, and I'll just measure those forces. And that's a really good idea, but unfortunately, that's going to give us the interface forces. And the interface forces are a property of not only the steering gear, but also the dynamics of the rest of the vehicle it's attached to. So let's say I want to take the steering gear and put it in a different vehicle. I can no longer use those interface forces because they already contain some of the dynamics of that first vehicle. So instead of the interface forces, here at Vibes, we like to use blocked forces. And to understand the concept of blocked forces, let's take that steering gear and put it on a really rigid test rig. So I'm going to put some force gauges between the steering gear and the test rig, and then I'm going to measure the forces during the steering gear operation. Now you can see how the forces I get are going to be a property of only the steering gear, because there's no other dynamics within the system to affect those forces. So these forces that I capture, I can apply them to any vehicle that has the steering gear installed. Now, this sounds like a really good idea, but I'm not going to be able to find a test rig that's rigid enough up to those high frequencies that I'm interested in. So instead of that, let's just use the test rig that you already have down in the lab. We're going to put some accelerometers around those interfaces, measure those while the steering gear is operating, and then we're also going to do an FRF impact test so that I can understand the relationship between force and acceleration. Now, this method is also going to give me the blocked forces so that I can apply them to any vehicle with the steering gear installed. So now we have a really good description of the forces. Now we also need a transfer path that we can apply those forces to so that we know what the driver will hear inside the vehicle. So if you already have the steering gear installed in a vehicle, you can just go out and do a measurement. So put some accelerometers near the seat rail and some microphones in the car and just measure that relationship to the steering gear. However, if it's early in the design phase, you're not going to have a vehicle ready to do measurements. So instead, this is where we like to use dynamic substructuring. With dynamic substructuring, we're going to build component models of all the individual components, and then we're going to tie them all together to predict the overall system dynamics. Using this approach, for the more simpler components that are, say, made of metal, really simple geometry, really easy to model, we can just use a computer-based model and get really accurate results. However, for some of the more complicated parts, some of the parts with really complicated damping or material properties or whatever it is, we can use test-based models. And using dynamic substructuring, we can combine all these computer-based and test-based models. We can also incorporate the dynamic stiffness of those rubber bushings that might be in place to provide some vibration isolation. So using this approach, say the design of one of these components changes. If you're not using dynamic substructuring, you'll have to go out and build up a whole new vehicle and do another test. Using dynamic substructuring, I just replace the component model of that individual component, and I get another full description of the system dynamics. We can also study what would happen if we were to change the stiffnesses of those rubber bushings and how that would affect what the driver hears. So we have a really good way to characterize the forces, we have a really good way to characterize the transfer path, but I have a component model from the computer, and I have one from the test, and I have this test rig, and how do I put all these things together? So this is where we use the virtual point technology. So with virtual point technology, Let's think of those interfaces between the individual components. There's probably a hole with a bolt to connect the two. I'm not going to be able to put test equipment right at the center of that hole where the interface truly is, because there's a hole there. So instead, I'm going to take my traditional test equipment, I'm going to put it around that interface, and I'm just going to do a regular measurement like that. Now, I'm going to transform that data to the virtual point right at that interface, and using this method, I can get translations as well as rotations directly at the interface I'm interested in. So you can see how using this, we can tie together those computer-based and test-based models. I can take the forces from the test rig and apply them to this system model, and I have a lot more freedom to work between the different components. And of course, this virtual point technology is integrated into all of our software here at Vibes. So hopefully now you have a little more insight into how we do sound and vibration engineering here at Vibes.